Ever wondered why, when you toss an apple in a moving train, it lands back in your hand and not at the back of the carriage? This seemingly simple question opens up a Pandora's box that leads us into the fascinating realm of physics and the concept of inertial frames of reference. An inertial frame of reference in its most basic form is a perspective from which an observer can see the laws of physics in their simplest form. Newton's first law of motion, which states that an object will stay at rest or move in a straight line at a constant speed unless acted upon by an external force, holds true in this frame. But here's the catch. An inertial frame of reference doesn't have to be stationary. It could be moving at a constant velocity. Take a train speeding along a straight track, for instance. From the perspective of someone on board, the train is an inertial frame of reference. Now, imagine there are multiple trains, all moving at different but constant speeds. They're all inertial frames of reference, moving uniformly relative to each other. If an observer in one train sees an object moving at a constant speed, an observer in another train will see the same object moving at the same speed. Inertial frames of reference are a cornerstone of physics. They enable us to accurately predict the motion of objects. But what about when we're not in an inertial frame? That's when things get a little more complicated. In a non-inertial frame of reference, we have to consider the effects of acceleration. Picture a carousel spinning around or a car taking a sharp turn. The forces at play here, such as centrifugal and Coriolis forces, make the laws of physics a little more complex to navigate. To illustrate this, imagine a spaceship cruising through the void of outer space at a steady speed, or a car driving straight down a long, flat road. Both of these are examples of inertial frames. However, a person on a spinning carousel or an astronaut in a space station orbiting Earth are in non-inertial frames, where the forces of acceleration come into play. In conclusion, whether you're tossing apples in a train or observing stars from a telescope, understanding inertial frames of reference helps simplify the complexities of motion and force. It's a key principle that underpins much of what we know about the physical world.